Welcome to the third part of our PyTorch tutorial course here on BrainOmega. In the previous parts, we explored the basics of tensors and operations, and today we're going to dive deeper. We'll see how PyTorch works seamlessly with NumPy, one of Python's most widely used numerical libraries, and then we'll cover reproducibility, which is the key to running experiments that give the same results every time. And don't worry about typing out all the code yourself. Every example you see in this video is available on our GitHub repository. You'll find the link in the description of this video. So, open up your notebook, follow along with the code, and let's get started. Let's start by converting a NumPy array into a PyTorch tensor. When we use torch from NumPy, PyTorch does not make a copy of the data. Instead, it creates a tensor that points to the same memory as the NumPy array. That means the two objects are linked. If you change one in place, the other will reflect that change. Another important detail is about data types. By default, NumPy creates arrays with float 64 precision, while PyTorch usually prefers float 32 for speed and efficiency. So if you want to match PyTorch's defaults, you'll need to explicitly cast the tensor to float 32. Now let's explore the difference between in-place and out-of-place operations. If we make an out-of-place change, like reassigning a NumPy array to a new value, it creates a new object in memory. Since the tensor was linked to the old memory, it doesn't see the change. On the other hand, if we modify the NumPy array in place, meaning we update the values directly in the same memory, then the tensor instantly reflects the change. This distinction, out of place versus in place, is really important when working with shared memory. Let's reverse the process and convert a tensor into a NumPy array. When we call .numpy on a tensor that's on the CPU, PyTorch again shares the memory instead of making a copy. That means if you update the tensor in place, the NumPy array updates too. But if you reassign the tensor to a brand new object, the NumPy array is still pointing to the old memory, so it doesn't change. This behavior is very efficient because it avoids unnecessary copies, but you have to be mindful about when you want a true copy versus when sharing is okay. If your tensor lives on the GPU, NumPy can't directly access that memory. That's why calling .numpy on a CUDA tensor will raise an error. The correct way is to first detach the tensor from the computation graph, move it back to the CPU, and then convert it into a NumPy array. Now, let's talk about reproducibility. Machine learning models rely heavily on randomness. For example, random weights when starting training. That randomness is great for exploration, but sometimes you want your experiments to be repeatable, so you and a colleague can get the same results when running the same code. To achieve this, we need to set seeds for every random number generator. Python's built-in random, NumPy's random, and PyTorch's random number generators for both CPU and GPU. PyTorch also gives us deterministic mode, which forces certain operations to run the same way every time, although it can slow things down. To wrap everything up, here's a single cell that demonstrates all the key points: reproducibility, converting between NumPy and PyTorch, memory sharing behavior, and seeding randomness for repeatability. This is the kind of cell I keep at the top of a notebook when I want predictable results every time I run it. And that wraps up the third part of our PyTorch tutorial course. We've learned how to convert between NumPy arrays and PyTorch tensors, the difference between in-place and out-of-place operations, and how to make our experiments reproducible by setting seeds. If you found this lesson helpful, don't forget to give the video a like, share it with your friends who are also learning PyTorch, and most importantly, subscribe to BrainOmega so you don't miss the next part of the course. Thanks for watching, and I'll see you in the next tutorial.